So in Calculus 1, or perhaps in Calculus 2, we introduced the idea of the density of a one-dimensional object like a rod or a wire. And with that single variable density function, we did a single integral to calculate the total mass. Whee! One day I'll figure out why it does that. I still don't know. Single variable density function, integrate to get the mass. Now we stepped up from having a wire to having a thin plate, which was a fundamentally two-dimensional object. And we found that if we had a density function, rho of xy, now we could integrate that over the 2D region occupied by the object, and from that we could get the total mass. But most objects in our reality are three-dimensional, so it seems like we should be able to integrate a three-dimensional density function with something perhaps that might be called a triple integral and get the total mass of the three-dimensional object. And that's what we'll be working toward here in the later part of chapter 12, talking about a topic called a triple integral, used to do things like calculate the mass and the center of mass of a fully three-dimensional object. Now, just like with double integrals, we're going to have to be able to build up some skills to even get started on those calculations. The first thing that we're going to do is use partial integration to evaluate something called an iterated triple integral, just like we had iterated double integrals in the previous sections. The next thing that we're going to want to do is we're going to want to be able to rewrite triple integrals over three-dimensional regions as iterated integrals so that we can actually calculate them. So that's the same process that we did with double integrals, except going up just one more dimension even. Now, to demonstrate the method, I'm going to walk you step by step through a particular example here. We're integrating from 0 to 2, 1 to x, 0 to xy, the integrand consisting of z plus x plus 2y, first with respect to z, then with respect to y, and finally with respect to x. Now, as in the case of a double integral, triple integrals are calculated from the inside out. So the first thing I'm going to start on is this integral from 0 to xy of z plus x plus 2y. Now, when we are working on the dz integral, just as before, we treat the other variables, the ones that are not active, x and y, as constants, as we did when we were doing partial derivatives as well. When we did the partial derivative with respect to z, we treated both x and y as numbers. Same here. So I'm going to do the inner integral, which is the integral from 0 to xy of z plus x plus 2y dz. Now, one thing that you'll notice me do as I'm working on these triple integrals is I'll actually work on the integrals one at a time. This is to avoid having to carry around the outer two integral symbols and their notation. And I just find that if I don't work on the integrals one at a time, the amount of writing that has to be done, I just fill up pages and pages of writing. So I clearly notate this is the inner integral, this is the dz integral. I try to keep my work clean and organized, but I also do work on the integrals one at a time so that I don't have to write so much. Now, if I take the antiderivative with respect to z, one term at a time, z will become z squared over 2. X is just a number, so it will become x times z. And 2y is just a number, and it will become 2y times z. And I'm going to evaluate that from 0 to xy, as z goes from 0 to xy. So if I plug in xy, I get from z squared, I get x squared y squared. Then x times xy becomes x squared y. And then 2y times xy becomes 2xy squared. And plugging 0 in for z causes all three of these terms to vanish. Now, having calculated the inner integral, I'm going to move one layer out to the next integral. Now notice at this point z is completely gone. When we finish the dz integral, all the z's should have vanished if we did our work correctly. Same principle that we used for double integrals. So now this is really just a double integral, and I'm integrating from 1 to x with respect to y. So here is the middle integral. Integrating from 1 to x, the result of the inner integral and the middle integral is taken with respect to y. So we have x squared y cubed over 6. We have x squared y squared over 2. We have 2xy cubed over 3, evaluated as x goes from 1, y goes from 1 to x. Okay, let's go ahead and plug in y equals x, and plugging that in we get x to the 5th power over 6th, and then plugging in x to x squared y squared we get x to the 4th power over 2. Plugging in y equals x to 2xy cubed we get 2x to the 4th power over 3. And then let's subtract what we get when we plug in y equals 1. Plugging in y equals 1, we get negative x squared over 6. Putting in y equals 1 to the second term, we get negative x squared over 2. And plugging in y equals 1 to the last term, we get negative 2x over 3. Okay, now there's a little bit of cleaning that we can do to make the next step easier. Let's combine some like terms. So for example, we have x to the 5th power over 6. We have what looks to be 7 over 6, x to the 4th power, and then x squared. It looks like we're going to have negative 1 minus 3 minus 4 over 6 minus 2/3 x squared, and minus 2x over 3. All right, almost there. The only thing that's left for us to do is to integrate with respect to x. So let's finish this with the outer integral. The integral from 0 to 2 of x to the 5th power over 6 plus 7/6 x to the 4th power minus 2/3 x to the 2nd power minus 2x over 3. And if we take the antiderivative, we get x to the 6th power over 36 plus 7 over 30 x to the 5th power minus 2 over 9 x to the 3rd power minus 1 over 3 x to the 2nd power, evaluated as x goes from 0 to 2. Now if you plug x equals 0 into any of these terms, they will vanish. And so plugging in x equals 2, we get 2 to the 6th power over 36 plus 7 over 30, 2 to the 5th power, minus 2 over 9, 2 to the 3rd power, minus 1 over 3, 2 squared. And you can simplify this if you like, but I don't think it's necessarily a productive use of time. So for example, on the exam, you're free to leave it in this format. Now, double integrals had 2 possible orders of integration, but triple integrals have 6 or 3 factorial possible orders of integration. And when you're setting up these triple integrals yourself, there are some syntax warnings here as well that you should keep in mind, because if the triple integral that you create violates any of these conditions, then guaranteed something has gone wrong somewhere, and better that you catch it early then you catch it after you have done a page worth of calculations such as this. So the first principle is the same as it is for double integrals. The outer limits of integration should just be numbers. The outermost limits are not allowed to be containing any variables whatsoever, just numbers. Now the middle limits of integrations, this can be a constant or it can be a function of the outer variable, but it can't have anything to do with the middle or inner variable. And the inner limit of integration has the most freedom at all. It can be a constant or it can be a function of the outer and middle variable. So let me give you an example of what I mean. Now this is nonsense first of all, because this is supposed to be a function of 3 variables, but that's just a typo. The main error in this setup here appears right here, with this z appearing as a limit of the middle integration. Now here we have dz entering as the inner variable, and its limits are in terms of constants, x's, and y's. That's fine. The outermost limit should be a constant, and here we have 3 and 1, and that's also fine. But the middle limits of integration are only allowed to be constants or functions of the outer variable, which means that numbers are allowed in this position, and y's are allowed in this position, so this function is okay. But the z as the upper limit of integration is not okay, because that is an inner variable, not the outer variable. So that's disallowed. If you find yourself writing something like that, you know for sure, automatically it must be incorrect. Something has gone wrong, and it's time to stop and go back and try and find that.